Welcome back to another LeetCode video. Today we're looking at LeetCode number 10, regular expression matching. It's a hard problem and we're going to try to solve this. So given an input string S and a pattern P, implement regular expression matching with support for dot and star, where dot matches any single character and star matches 0 or more of the preceding element. The matching should cover the entire input string, not be a partial match. Okay, and it's guaranteed that our string has at least one character and that our match, our pattern, also had at least one character. Furthermore, the string contains only lowercase letters and P contains only lowercase letters, including the dot and the star. It is guaranteed for each appearance of the character star, there will be a previous valid character to match. Okay, but that could also be a dot, right? We could have dot star, so match any number of characters. But I guess it just means that star will never be the first character in the pattern string. I guess that's what that means. Cool. Okay, example 1. So we're given an input S, AA, and PA. So the pattern is we should match A, but it's not going to match because the pattern is shorter than, well, not only is it shorter, but also it only matches a single character, but our string has 2 characters, right? Okay, now, second example, we have the string AA, and we have now the pattern A star, which means that we can match an arbitrary number of A's, including 0 times A. So we start with the pattern A, so we can match that A, and then we learn that we can match it an arbitrary many times, which we will do, and then that's a match. Third example, so we have the pattern AB, and now I have, we have the string AB and the pattern dot star, which means dot matches any character, in this case A, and star means any character, it doesn't mean A again, it just means any character for any number of times. So we can match the entire string with dot star. Cool. Yes, so how do you approach this? I have solved this a while ago, but not recently. So let's see, let's try to do this again. So I would say, no, I'm thinking about, whether we should handle any edge cases, for example, when the string is longer than the pattern and the pattern doesn't contain any stars. That would mean we don't have a match, right? But maybe we don't have to deal with that case. Maybe all we need to do is proceed character by character. And as we've seen, we should probably have a little look ahead that checks if the next character in our pattern is a star, because that gives us some information about what we can match at the position before the star. And I also think that we're going to need some backtracking, because we could be matching a string prefix, and then let's see. Let me give you an example. So if we have, for example, the string AB, and we have the pattern A or dot star B, like so, we could match the entire string with the first 2 characters of the pattern, and then we have nothing else to match the B. But we could also just try to match the first 3 letters of our string against this, the start of the pattern, and then the B. So obviously we need to try different lengths of what we can match when we use the star. I think it's called a cleany star, isn't it? Yes, so what I would say is we need some kind of backtracking. And backtracking tells me that it should probably be recursive. I think that we will iterate over the string and the pattern. Well, we will iterate over the pattern in linear time, right? but then we will try different approaches to match things in our string S as soon as we have a star operator or a star in there. So I think the runtime will be O of, what would it be? I'm guessing O of n squared. I'm not 100% sure yet, but I think it's going to be O of n times n squared. And well, if we need to do backtracking, we need to remember probably previous positions. And that would probably be O of n space, where n is, I suppose, length of S and maybe the length of P combined. I think that would be an upper bound. But we will revisit this analysis later, just to make sure that it's correct. But this is what I'm getting at right now. So yeah, I would use, I would do a recursive approach where we try to match the string against the pattern from a certain position. So we would match maybe, we have two indices, I and j maybe, and we start by calling this. So we say return match, and we start at 0, 0. So position 0 in the string and position 0 in the pattern. And now if we have this, that allows us to, in our example case, to try different matching. And I also think that it is very likely that we're going to call match with the same parameters multiple times while we try to match it. So we probably want to cache the result of a match. We don't want to recompute it all the time. So by caching the output value, giving the inputs I and j, this is a built-in Python function. You can also just say, have like a cache, a manual cache, and just say if I, j in cache, return cache with the key ij. It's basically the same thing, and we would have to write it into the cache. The result of this method call, we would have to write it into the cache if it's not already in the cache. So, but I'm making it a little bit easier. So I'm going to do this. And, well, so we have a I and a j. Now, what do we do? Well, I think we should try to match, right? So we could say if character at position, well, the character and the pattern is equal a dot. We need to take care of that case. We need to take care of the case if the position at I plus 1 is a star, right? That's another case that we need to take care of. And we also need to take care of the case if the pattern at position j is the same as the string at position I, that's a match as well, right? Now, the order of trying to match them, I think, matters. So we should first do the look ahead. Obviously, for that, in order for that to work, we have to also check that basically j plus 1 is smaller than the length of the pattern. Otherwise, we're going to try to read a character from the pattern that is outside of the pattern itself. Then we are going to j plus 1 should be smaller than the length of k. Yes, I think that makes sense. And now when we know that the next character in the pattern is a star, well, the next thing we want to know is the previous character a dot, right? Because that means we can match any number of characters in any kind of character from 0 to as many as there are times. So now we check if, well, if the pattern at position j, is that a dot, right? So we have to check that. And if it is, well, that means we can iterate over all of the characters that are remaining in our string S and try to match it from there. So what we do is we match from range I for k in range from I to the length of the string s, right? Because if we start at I, that means basically we're using this 0 times. If match from j plus, no, sorry, from I plus, or simply from I plus 1 to j plus 2, because we need to jump over the dot and the star and continue trying to match things after that with our pattern. So if that returns a match, we return true, right? And if that doesn't return a match, we can, well, actually, why am I doing +1 here? Let me see. Do I have to do a +1 here? No. We can match from from k. Yes, I think we should be good like this. Yes. All right, so if that is the match, then we're good. Yeah, then we're good. Return true. And I apologize if this is going a little slow. That's because I'm trying to solve this right now. So k starts from I. If it's at I, that means we're not going to match anything. We're just going to, we basically use 0 times, matches 0 or more of the preceding element. So for k equals I, that's 0, but we still have to jump over the dot and the star in the pattern, and etc., etc. And then we continue from there on. Now, what else can we do? Well, we don't really have to do anything else, right? So that's how we handle that case. Now, the other case is else. If pj is not a dot, we basically have, well, that basically means that we have to actually match up to from k to I to length s, from I to length s occurrences of the preceding letter. Right, so what we'll do now is we'll just have another loop for k in range I length of s if the string, if the character in the pattern at position j, which is not a dot, is equal to our string s at position k, that means that's a match, right? But if that is not the case, we're done. So we should break if that is not the case. Break. Just gonna write this way. Then we break. But if it is a match, we can actually now try to match from that position. The cleaning star gives us the option to match 0 to however as many matches we have. As soon as we don't have a match anymore, we're done. We need to break out. But otherwise, we can actually call match recursively and try to match the rest of the string again. Match, let's say k. Well, now we have to advance. Well, we actually have to go from k, and also we have to jump over the character and the star in our pattern. And if that is true, we return true as well. Yes. We're matching from k, I, yes. Okay, and that's pretty much it. That is pretty much it. Cool. And yeah, so now what about the other cases? So if I'm going to put an else if here. So if we had a star, we try to match from there on. If we can't match anything with the star, we basically have to say we did not find a match. So here we return false. Now, we don't want to try these other cases if the first one here failed, right? So, but now we can deal with that case, and that case is also very simple. It just means match any character in, let's see, we just match any character in our string. So what we'll say is we can just jump over I, so we just do I plus 1, and we say j plus 1. So, and we can just return that. It will either return true or false. And also, the same case where the same. Well, basically, all we have to do, we do exactly the same. Dot means match any single character. So we could actually combine these two cases, and we could just say if we have a dot or the characters at the positions match, it's a match, and we can advance both in the pattern and in the string. Right, and yes, just thinking about how could I write that a little simpler. No, I think we should do it like so. All right, so now what is the case where we basically want to terminate the recursion? Well, that is exactly true when I and j are the length of their strings, right? So if I equals length of string and j equals length of the pattern, turn true. Yes. And I think that is all we need. So that is the base case. We should probably walk through an example now to see if we made any mistakes here. So let's use maybe this example. So we have the string s, it's AA, and we have the string p, which is a star. So we're trying to match from 0. The first if statement is false, so we're not returning anything. Now, j plus 1 is smaller than p, and it means it's pointing at a star. So that is actually catching that case. Now the next is to check if at position j, at position 0, if we have a dot, we don't, we have an a. So that case doesn't catch, but this one does. So now we're going to iterate with k from 0 to 1, because the end 2 is not inclusive. So k assumes the values 0 and 1. First we check if the position at j, which is the a, is unequal to the string at position k equals being 0. So they're not unequal, so we're not breaking. So we're trying to match. Let me just see. Oh, I see a logic error here. So actually, we're trying to match from position 0. And for the case that we try to have 0 or more of the preceding element. So actually what we have to do is we have to, well, we have an off by 1 error here. I think what we should do is if we have a match, then we need to jump over that match and continue. But we also in the end need to have a case where we basically perform 0 matches. So we have to basically say return match and at position I and j plus 2. This is where we have 0 matches. When we do this, that is actually at least 1 match or more, right? So yeah, so that's what we need here. And I think we also need the same in this case, where we jump over the matching character here. And if we're not matching 1 occurrence, we're going to try to match 0 occurrences. Well, 0 occurrences doesn't happen in this case. So let me think. matches any single character. So there's no zero occurrence here. But we can, because we have a star, it means we can have zero occurrences of any character. So we actually need this here as well. Yeah. Okay. Now let's continue with the example. Where was I? So we are here. So we are trying to match, well, the first characters coincide. So P at J is not unequal S at K. So we go into the next one. We advance our pointer in the search string, but we jump over the pattern. So A has not reached the end of the list, but P has. And we're not covering that case here. So if J equals length P, or we have to do both cases. If J is length P and I is smaller than length S, we return false, right? Because we ran out of pattern, but we still have a string to try that we need to match. Yes. So if J is the length of P, well, we can probably simplify this. We just return if I equals the length of S. So whenever we reach the end of the pattern, that means we're going to return whether we've also reached the end of the string. And in order to have a match, this needs to be true. Cool. So we run into this case where J is the length of the pattern, but I is not the length of the string. So that returns false. And we're back into our loop. And now we're increasing K to 1. So we actually match two occurrences. Oh, sorry, we're here. So now K goes to 1. We still have the same character at position 1. And so K is now I plus 1, and we pass in basically I plus 2, which is the end of the string, and then we have a match, and that should work. All right, cool. So I think that example works. What about this example? I think that should work exactly the same because the code is also structured kind of the same. Except that we don't have the character comparison because we don't really care what character there is. Because we can match any, right? Why this one is unique here, it's not here. All the rest of the logic is exactly the same, so I'm not going to test that code. Yes. And I also don't think we need to test anything here. So I would say this is pretty much the solution. And in terms of runtime complexity, so we have a recursion. Well, first of all, space complexity, you can see that match can be called with, well, pretty much any combination of characters. So it's fair to say that space complexity could also be O of n squared in the worst case. Yes, it could be O of n because... Yes, it could be. If we just had, for example, dot star as the pattern, and then we would try all different versions of substring to matching all different substrings of the string S from every starting position in the string S. So that's definitely O of n squared space that would be cached here. And in terms of time, it is... let me see. So we have, so what is the branching factor? We have a recursive call. And then we could have a pattern that is dot star, dot star, dot star, dot star, or something. So that we always iterate over all of the length of the elements in here. I'm actually not quite sure how the caching influences that. But in the worst case, this is an O of n operation in the length of the string. And yeah, I guess we need to separate the length of the string S and the pattern P. And I'm not 100% sure how are we going to do this. I think it's O of n times m times n. I think it is. So it's probably something O of n cubed and O of n squared space. Something like that. Yeah, I don't know. I don't know if this analysis is good. And my brain is currently a little bit fried. Still a little bit under the weather. Anyways, yeah, let's try this. See if we made any syntax errors. No syntax errors. Cool. And now let's try to submit this. And we have an index out of range. If match return true, pj pi. Interesting. So how can j ever get larger? And here we have the example string AB, and we're trying to match dot star C. So first we're going to try to match dot star against the whole string AB. But then we get back false in this case. J plus 1. Maybe we have to check if j is larger. If j, or we have to add this check here. So we could check here if j is larger, then we return false, or we add the check here, right? If, well, it's either j or s. If I is smaller than length of s and this. And j is smaller than length of pattern. So let's use this as an example. S equals AB, and we have P equals dot star C. I'm not just going to run this example. And what are we getting? We're not getting an index out of bounds error anymore, which is nice. So I think that was the edge case that we had to have to consider, because we're increasing j plus 2. Yeah. I think it's because j is going too large, not I. So, but this probably doesn't hurt. Yeah, there we go. And now let's just double check if it's really just j that is too large. No, it's not just j. Could be I as well. Cool. Yeah, anyway, so that's this problem. Well, what did we learn from this? So this requires careful consideration of, how to handle the cleaning star to match any number of characters, and you handle that by using a look ahead to look at what's the next character. Of course, you then have to check whether there is a next character. Then you basically try to check. Well, then you have to check if it's a dot or an actual English letter character that is the predecessor of the star. And the order also matters. So you first have to check whether you are going to have a star one step ahead before you try to match the current characters against each other. So if you have a star, you need to handle that first. After that, you can handle the dot, etc. Yeah, and very important to use the caching. If I remove the caching and I run this, and I submit this, we should get a timeout error, because we're recomputing the same stuff over and over again. Yeah, you can see. Oh, actually not. Okay, that is interesting. Well, maybe they were just kind with the test case, but I would add it just to make it more efficient. So this is now running almost 7 seconds. And with the caching, let's see if there's a, yeah, it's just milliseconds. So it saves us a bunch of computations. All right, that's it.